Hey everyone, this is our first video on the unit of waves. Now our first topic actually won't be about waves, it's going to be on something called simple harmonic motion. We're going to define what that is and then see how it applies to masses on springs and on pendulums. We're also going to go over two terms that we haven't talked about before, period and frequency, which many of you are probably already familiar with. All right, to start off, the definition of simple harmonic motion. It's kind of a scary seeming string of words, simple harmonic motion. It's really just referring to objects, things that have a motion that is oscillating, sometimes called periodic. It's going back and forth and back and forth and back and forth. All right, for example, think of a mass attached to a spring, or imagine a pendulum that you pull back and you release. They swing back and forth and back and forth. The cause of this back and forth motion is due to a restoring force. For example, when I have a mass attached to a spring, we know that there is a force of kx acting on my mass from the spring itself. And remember, that force is always in the opposite direction that that spring is either stretched or compressed. So for this mass right here, if I stretched it to the right, well, the force is going to pull it to the left. But then when the mass is sliding to the left and it compresses, all of a sudden that force is now to the right. It's restoring. Kind of makes it want to go back to where it was before. So you have this continuous back and forth motion. I have a visual right here. Here we see a mass, a blue mass attached to an object, a spring, that's going back and forth. This is what I mean. This is simple harmonic motion. That blue block is just going back and forth and back and forth and back and forth. Okay? Well, like I said, we'll look at springs and pendulums. For a pendulum, what do you think the restoring force is? What makes the pendulum, and we have like a mass right here. This is sometimes called like the bob, B-O-B, of the pendulum. But what would make the pendulum go back and forth and back and forth? It's actually just the weight. It's the pull due to the force from the earth. That's the restoring force here. So it's really just motion that's going back and forth. It's oscillating. Well, the first type, as we already saw, were masses attached to springs. Very quick reminder about ideal springs. It's something that follows Hooke's law. It's really just an equation. We'll assume most of our springs in this class are ideal unless it says otherwise. Remember, there's a minus sign. That just means that the compression or the stretching is in the opposite direction of the force. On the AP test, they actually put this equation in absolute values because they really don't want you to be confused, hopefully. Hopefully that's the reason. They don't want you to be confused about the direction. Don't forget, though, that if we were going to set up a Newton's second law type problem, if I wanted to draw a free body diagram, so I have like this mass attached to a spring, let's say it's at rest right here, you just lowered it down so it's not moving. Well, I have the weight of that block, mg, and I have, not tension, because it's a spring, I would call that the spring force. Normally we say up is positive. If I was doing the sum of the forces in the y direction, remember, don't just stick in that negative sign there. If you're saying up is positive, this spring force right here would be tugging upwards. So that's Fs minus mg. Again, in this case, it's at rest, so that would add up to be 0. Just remember, keep our forces, when we do the sum of the forces, the same as usual. Don't think you have to stick in a negative sign. But where I really want to talk about masses attached to springs is in our first new term, which is period. Remember, if I attach a mass on the spring, we saw this right here, we have this simple harmonic motion, this oscillation going on. One thing we could do, one thing we could measure is the time it takes for one cycle. And that's what the term period comes into play. Period is a particular time for this back and forth motion. It's defined as the time for one cycle. Now, what exactly is a cycle? It's one full motion, not repeating. What I mean by that is I take this mass, I pull it back on that spring, I let it go, the mass is going to go this way, and then this way, and now it's back where it started. This time, there and back again, that's the period. Again, with my animation, if I reset, we're starting right here. The period is from there to there, when it gets back to where it started. You could pick where you start. I could look over here. So the period would be here to here. And if I had a stopwatch, I could time that. It's just a measure of time. So because it's a measure of time, we'll use the letter t, but they give it an uppercase T because it's a very specific time. It's the time for one cycle. The units are seconds. All right? There's another thing we could measure, and that's the frequency. The frequency is how many cycles in a given amount of time. Instead of timing how long for one cycle, we could count how many cycles it does in a certain amount of time. And here's what I mean. Here's how we could figure out the frequency. I'm going to reset here. Let's count how long, let's measure, the time for 3 cycles. 3 there and backs. All right, so there's my stopwatch and start. Here's 1 cycle. 2 cycles. 3 cycles. Ooh, 3 cycles in 7 seconds. So the frequency is 3 cycles in about 7.7 seconds. Well, cycles doesn't really have a unit. It's just a number. It's just a counting. Of course, if you had a calculator, you could get an actual decimal. But that's why the units are a little weird. It's just 1 over seconds. Looks like I have too many seconds right there. I don't know why I wrote it twice. All right, 1 over seconds. That's given the special name of hertz. So this is 3 over 7.7 Hz, hertz. Okay, again, if you have a calculator on hand, you could figure out what that decimal is. Well, frequency and period are very similar. They're in fact inverses of one another. If you know the frequency, just by taking the inverse, you can find the period, or vice versa. Remember, the period is the time for one cycle. Frequency is the number of cycles, in a given amount of time. All right, next thing. If we have a mass on a spring, there's an equation that will allow us to calculate the period of that motion. All we need is the mass, m, and the spring constant k. That alone will allow us to figure out the amount of time. And what I already wrote over here, remember, frequency is 1 over time, 1 over the period. So if I can calculate this, this is on the equation sheet. We already have an equation for frequency. You kind of get 2 equations for the price of 1. All right, what I have right here is the letter x. Notice what is not in the equation. How far that spring is being stretched does not affect the period. I can show you why. Let me go to this other animation. Right now I have this mass stretching a spring starting from this spot here, a certain distance marked with this little spot. I'm going to clear this. Let's time how long it takes for this mass to go there and back, 1 period. Here we go. It's going to go up. I'm going to time 1 period and stop. Let's look, 0.83 seconds. But let's reset. Instead of pulling it back that amount, I'm just going to pull it back here, significantly less. Let's see if the period is smaller. Well, let's try. Up and back, down. Oh, look at that. You get pretty much the exact same period. How far you stretch that spring did not affect the time. You could maybe rationalize this because if you're pulling it back more, there's more force, therefore more acceleration, makes it speed up. It kind of makes up for the fact that it has a larger distance to travel. But the period for a spring, a mass on a spring, does not depend on how far it's stretched or compressed. Okay, we're almost done. For a pendulum, all right, if we take a pendulum, again, this is a mass attached to a string or maybe a thin rod. We won't worry about the mass of the string or the mass of the rod. We're going to pull it back some amount. The amount we pull back is usually referred to as the amplitude. It's often given as the angle, all right? And again, we could time how long it takes to go back and forth. I even have an animation of that. I could pull this back and let it go. Aha! So here's my basic pendulum. I could get a timer going, a stopwatch. And we could time how long it takes for 1 period from there and back, about 1.64 seconds. All right? Well, the time for a pendulum, the period for 1 cycle is 2 pi L over G, where this here is the length, and this is just the acceleration due to gravity. Oops, acceleration due to gravity. Notice what is not on here. The mass that's attached does not affect the period. I could again check that using my Phet simulator. I had 1.64 seconds. All right, I hit pause. Let me drastically increase the mass. Or actually, let's make the mass really tiny. Let's see if I get 1.64 again. I'm going to restart. Let's see if it's 1.64. Ooh, pretty close. All right, if I make the mass huge. Sorry, I wasn't great at timing. Let me reset. Let's try it. Ooh, well, not great. But I'm getting around the same values, 1.64, 1.76, 1.8. All right, the period stays the same. It does not depend on the mass. So that's really it. We've looked at period, we've looked at frequency, we've seen springs, masses on springs, pendulums, the equation for each of those. We'll get more practice with this simple harmonic motion as we do some practice problems. Thanks for watching.